Okay, well, we're happy to have Koushik here. He is from the Black Hole Initiative at Harvard, and he's part of the Event Horizon Telescope collaboration. He does simulations of black hole accretion, EX, all that kind of cool stuff, using Jeremy C simulations with GPUs and all that good stuff. So any of that interests you, please talk to him. He will be moving to Maryland in the fall. So we're happy to have him here. He just happened to be in transit. We're happy to arrange this. So
yeah.
Take it away.
Thanks, Sean. And thanks for arranging this so quickly. I hadn't planned on this, but awesome. It is just very nice to visit here, I think. Just getting the opportunity to speak to people here. Today, I'll be talking about having very strong magnetic fields around black holes and how that sort of changes the flow structure, as well as there might be interesting observational consequences of having strong magnetic fields. I'll be focusing mostly on EHT stuff, but since these simulations are scale-free in the sense that we don't exactly prescribe a mass to the black hole, and so everything scales. The results in general can be scaled up from supermassive black holes all the way to X-ray binaries, but only in the hard state where radiation does not play a significantly big role. So getting things started with Chatterjee star, which is the galactic center black hole. This is I think a radio image from Meerkat, one of the more high definition ones. Chatterjee is right in there among all of this mush with supernova remnants and other knotted structures in there. This is a spectral index. Yes, a spectral index plot. And basically what the interesting features over here is that other than the central engine, you also have these very bright, long filamentary structures, which nobody knows where they came from. And so people are possibly sort of thinking about whether they are somehow connected to the central engine or not. And earlier, last year, the Event Horizon Telescope collaboration finally came up with this image from 2017 of the central black hole inside a star. Basically, the main thing over here is that there's a ring-like structure with a central depression. The individual structures over here should not be trusted, just because we didn't have the right both spatial resolution and temporal resolution to sort of say that these structures are really there. But it does help us when we are comparing our simulations to the actual observation. Other than that, why Chatterjee is so unique for for simulations, particularly of black holes, is because of what it looks spectrally. So this is the multivariate spectrum of Chatterjee star, power versus observing frequency. And all of these points are different data points. So going from the radio, far infrared, near infrared, and then X-rays over here. So what people have mostly found by feeding semi-analytical accretion models is that a bulk of the emission, especially a sub-millimeter, should come from in the vicinity of the black hole. And then, so this is all thermal synchrotron emission. And then this is inverse Compton from that thermal synchrotron. But there's an additional component that people think comes from electrons that have been accelerated by some mechanism. People are agnostic about what exactly. And that produces high energy emission, especially either at near infrared, given by this line over here, or in the X-rays, where this is the quiescent emission, which people think that comes from thermal bremsstrahlung at large distances around the boundary radius, if you're interested. But sometimes you can get very large fluxes known as flares in the X-rays. And it's generally thought that this component over here of accelerated electrons, that's the culprit, that emits, that population emits very high energy X-rays. So that's what I'm going to focus on because it could tell us a lot about what exact processes are going on near the black hole.
So the infrared isn't changing much with the X-ray force happening.
So that's an interesting question, actually. So apparently, whenever there's an X-ray flare, usually you find a near-infrared flare as well, but not vice versa. So it's not we are not entirely sure what's the origin of the near-infrared versus the X-rays. And if you look at near-infrared statistics versus X-ray statistics, they look different.
X-rays can't be due to a change in the response.
So usually, like this has been like the question for I think like the previous 2 decades. Like people have been trying to fit both the non-thermal synchrotron model as well as the SSC model over here to this sort of structure. Now they can fit it, but in order to get some amount of increase in the inverse Compton, you need a large increase in the submillimeter as well. That's the issue in general, I think.
Which is not seen.
Which is not seen. I'll be going into that a little bit. But before that, X-rays. So in 2019, actually, Dale Haggard from McGill University actually found 2 huge X-ray flares of the Chandra, one of which had this sort of double peak structure. So this is the quiescent, I think, with the nearby magnetar in orange. And this is a huge flare that she saw. And there's another flare over here. Now, the interesting part for this is that it's 600 times larger than the quiescent emission inside a star. And this one was 245. So these are the largest X-ray flares that have been seen from such a star. Now, big flares have also been seen in the near infrared. And this is the Doe et al. Paper, where I think the usual minimum flux that Cake can see is around 1 millijansky or so, 0.1 millijansky, and it increased to 60 millijansky. So this was a huge, huge rise. And additionally, gravity, which is a near infrared interferometer, also observed orbiting hotspots, not particularly for very large flares. I don't know if they have observed during a very large near infrared flare, but at least there was a significant bump in the light curve. So this is what you question, like about the millimeter and submillimeter. So these are Alma light curves taken as part of the EHT campaign in 2017. And the issue is that the radio or the submillimeter, like it fluctuates quite often, but the fluctuations are never that big. And basically, it's very hard to say what exactly a flare is when there's this constant noisy fluctuations. In the X-rays, it's very prominent where you have this quiescent level, which you know, and then you see like maybe a jump in by an order of magnitude, but it's never the case in the millimeter. Now, on April 11, 2017, there was an X-ray flare right before the EHT started observing, which was excellently bad. Because we didn't know what the submillimeter was doing during the X-rays and whether these two were related or not. But it did start observing right at the end and found that the X-ray flux the submillimeter flux sort of increased. So if we were to interpret this somehow as, let's say, a flare mechanism, and these two are connected, that could help us sort of pinpoint what sort of process can actually give us that signature. Yes, so yeah, looks depleted and climbs post X-ray flare. Now, additionally, this Wilges et al. Paper also detected polarization with Alma. And so what they did is they plotted what Stokes U and Stokes Q were, and they saw this loopy sort of behavior over here, which then they assumed to be, let's say, a flare which is represented by a hotspot like that, moving around a black hole, has some inclination angle, which was similar to what gravity predicted for the hotspots before, around 150, 160 degrees, and then assumed some magnetic field topology and at some radius between 8 to 13 m or gravitational radii. And what you can see over here is that this is the blob which is moving around the black hole, which is located somewhere over here. This is a ray traced image of that system. And this is a secondary image which came around the black hole, basically, where the light rays sort of bent around the black hole towards us. And this X, which I'm not sure if you're able to see, this is the centroid of the total image. So how the centroid is moving around depending on what the location of the hotspot is. And so because you can do polarized ray tracing of this system, what you can try out is what does the Stokes Q and Stokes U map look like, and try to fit that model of what we saw from the observations.
So sorry, what fields do you mention?
I think this was just probably some sort of power law they took. It was just something that to shine. Yeah, so I think over here they assume vertical magnetic fields for this one.
And the spot is somehow moving through the magnetic field.
And the what?
The spot is moving through the magnetic field.
Or at that part I'm not so sure about. I think yes.
It's like basically a background.
And they moved around?
Yeah.
Okay.
Okay. Also, it's basically a little geometrical model. But,
yeah. So this is not an MHDO model or
source
anything.
of circular polarization. That's what I know.
Mm-hmm.
Okay, go on. Sorry.
No, this is a good.
The red is the model and the blue is the observation.
Yeah, the blue is the observations and the red is the model. And the different T's are the different times. So basically you can map whether like this goes in a clockwise motion or anti-clockwise motion. No, there's
Polarized source. You can create circular polarization by transfer.
yeah. So the idea is that you just assume some spot
Yeah.
which has a certain size
Yeah.
and that has a certain emission model.
Yeah.
Moving through this field of, I think, background field of magnetic fields to produce the synchrotron emission.
But and this is linear.
Then it would be polarized.
Right. Yeah. Yeah, I think I'm not sure if they looked at circular from here.
Right.
Because the V is.
That makes sense.
Yeah. I'm not even sure they mentioned circular in the paper. I don't know. But so, for example, this was an equatorially moving hotspot, by which I mean that, let's say you have a black hole which is spinning like this. The hotspot is restricted to the equatorial plane, but you can also have hotspots which move helically out through some sort of outflow. But I don't think that has been used to do similar kind of stuff because it makes the problem more degenerate, I think. That's the issue. And then along with, so this hotspot has a sort of spheroidal type of structure. You can also get shearing hotspots that depend more on some structure of the velocity map that you give the hotspot. And this is work by Paul Tiede. And what we did in a recent paper is we compared how these hotspots exactly move, or the velocity profile. How does that map or how does that compare to the two general relativistic MHD flows in general? Just as a form of comparison, such that we can make better semi-analytical models out of the GRMHD. Yes, so that's the central question that we have. What are the mechanisms behind these flares and hotspots? And of course, why do we care? Because we care about particle acceleration. So what I'll be focusing on is, as a source, are magnetic fields and their relationship with flares. or probable relationship with flares rather. From the polarized image of polarized horizon scale image of M87, what we found that you really needed vertical fields to exactly have these EVPA patterns. You couldn't really fit the or explain the linear polarization without strong vertical fields. And just from such a start, if you do simulations, for example, and ray trace and figure out what the multi-wavelength spectrum looks like, without accounting for, this was a case where I didn't account for any synchrotron self-Compton, but only focused on a thermal synchrotron model and a non-thermal synchrotron model. And the conclusion was that you will really need a strong explosive events to explain the larger sort of X-ray flares, which happen. So this was the Doe et al. One, and this is the Haggard 19 But in general, you could explain moderate X-ray flares, that the average X-ray flare just from disk turbulence, like just what you the non-thermal activity that you expect from this turbulence. But what both of these results show is that you really need magnetic fields to explain the data, like strong magnetic fields. Now, what are the multiple sources of flares that we know of till now in our simulations? Well, one is just by the modulation of the accretion rate onto the black hole. When more gas is there, you get more emission. When less is there, you get less. And this turbulence, you can get some amount of fluctuations. As an example, I have a light curve, a sub-millimeter light curve from one of my simulations over here. And you see, if you look at the blue line over here, there are small scale fluctuations, which are mostly, the origin mostly comes from this turbulence. But you also see very large scale modulations of the light curve. And this happens because the accretion rate onto the black hole is changing over time. Yes, so other than that, there are on a more plasma physics kind of thing, you have merged plasmas, which can give you hotspots. This hasn't been totally studied yet, and only in recent simulations have we been able to actually resolve plasmod activity. But it's really difficult to actually figure out what the emission process is for these structures. And then magnetic flux eruptions, which I'll go into much more detail in this talk. These happen when you sometimes see flux tubes or magnetic flux tubes just get ejected into the disk. And then how these tubes exactly interact with the accretion flow, that can give rise to additional flaring sources, let's say. And then there are also shocks, both in the disks as well as in the jets, which I will probably discuss a little bit. So MADs, or magnetically arrested disks. This sort of system is what we call the saturation point of magnetic fields in black hole accretion. That is when you feed the black hole with so much magnetic flux that at some point the magnetic flux gets saturated around the black hole and you can't take in any more. What you see is, so this is the black hole, this is the accretion flow in the gas density in color. We sometimes see these dark patches which erupt out of from the vicinity of the black hole. So these are those magnetic flux tubes which get ejected from near the black hole, and after they get ejected, they go out, interact with the spiraling disk, and that's when you can get a lot of emission out of it, a lot of flaring system. So interestingly, if you, let's say, plot something like the gas temperature, which is this orange thing over here, but what you see is that in this depression region, or where the density is very, very low, you get very strong magnetic fields. And you also get a really very, very relativistically hot gas. And that happens because there's magnetic reconnection going on over there. And this region, this hot gas has the potential to emit in the X-rays and probably beyond, like maybe in TeV as well for MET7. But this is what we are trying to focus on, or at least understand what sort of emission do we expect from this? What is the emission from the accreting flow outside of this region, and how does this hot gas interact with the surroundings?
In your sims, do you have all these ranges of processes? Or?
No, that's the issue. That's the basic. So this is just some fluid that we have in the simulations. You can add in extra physics by assuming like a separate electron temperature model, which Sean does, where you assume some sort of plasma physics, which sort of divides up the energy between electrons and protons. So we can do things more consistently there. But my feeling is that you really need like local box simulations to understand what's going on, what the emission would be from there.
So that reconnection heat that you get there is numerical, right?
Yes.
Because you're doing ideal emission.
Yes.
And I think when you compare like resistive emission heat and ideal emission heat, you get more or less like consistent results, right? So I
mean, it depends on the resolution. Like if in the resistive simulations, if you reach the resistive scale, that is, if your numerical resistivity is lower than your explicit resistivity, then things become different, I think, because then you have a floor value in the resistive, which makes it more physical.
So like my question is, can you trust the properties of the gas?
Not the thermodynamic properties of the gas, but you can trust the magnetic properties of this region.
Yeah. Actually, my question is like, this is highly magnetized.
Yes.
So in principle, you need like some force field, the description of the thing. So yeah, can you trust that in like the other entity, even if it's like very highly magnetized? Because I imagine you get some reach some floors.
Yeah, so the temperature over here is determined by what floors you have. So for example, one of the floors is, or the ceiling is a magnetization, which in force free is infinite, but in our simulations is 50, 100, some max limit. And that is what sets the temperature that you get out of reconnection. Now so you can't trust the thermodynamics of the temperature exactly what you get. But what we tend to sort of do is ignore emission from these parts, which I'll get to in a bit, at least for the sub-millimeter. For the X-rays, if you really want to look at what the expected emission from this region would be, at least the first test would be to assume some sort of non-thermal electron population based on what the available energy is, I guess.
Thank you. Just could you say a bit more about what you were seeing magnetic field and how far out you start to flow and go? That obviously will influence what the magnetic geometry is close to home.
Yes. So typically, just because we want the simulations to have normal accretion and all, we start with polaroidal or like a large amount of vertical fields, so that everything accretes more or less very nicely and you get jets.
What sort of magnetization are you starting at?
Magnetization. The magnetization is very, plasma beta is like, you start out with a minimum plasma beta of, I think, 100.
Okay.
So that the magnetorotational instability can work, is magic. And after that, the plasma beta sort of goes down and down as you go near the black hole.
Right. And how far out do you start?
Typically, the simulations I do, the outer boundary is between 1,000 to 100,000 gravitational radii, and the size of the disk, at least for the typical MAT simulations, are like what, 100,000 gravitational radii, something like that. But of course, you can do like more bondy, more spherical type of flows where the entire region might have vertical fields. So yes, magnetic flux eruptions. So I just put this slide on just to show you what exactly a magnetic flux eruption looks like. So yes, so this phenomena or this structure occurs when the black hole or the black hole magnetosphere cannot hold on to the magnetic flux anymore. So it reaches a saturation limit. And what happens is magnetic reconnection around over here from near the black hole triggers an escape of vertical field lines, something like this. So this blue region, which the color shows density, and you can more or less say that the low values of density correspond to some flux eruption event, in this case, at least. So this is a initial expulsion of that flux tube. And what I'm doing is I'm tracking this specific flux tube and draw. So this is a horizontal or the equatorial picture coming in from top. And what you can do is look at the vertical picture as well. And you see this point over here, this break in the accretion flow. So that's where the flux tube exists, as like this. And then it sort of rotates around with the accretion flow, and it sort of gets extended or sheared out rather. And you can see that the tube basically goes like this, and what it does is it pushes against the gas, and that launches winds in this case. So there's some angular momentum regulation that's occurring due to the emergence of these flux eruptions. And finally, at the point where this structure or this field line, this bundle gets completely sheared out, you have escape of magnetic flux through the wind region. So because these flux tubes are sort of crashing into the flow, this could appear in the form of hotspots, especially in the near infrared. A couple of papers looked into that. So especially like these points over here, you have pretty hot gas. And yeah, like I said, that because the flux tubes are interacting with the gas, they're punching against the gas. The tubes can launch disk winds. They regulate angular momentum, especially in these magnetically arrested flows. And of course, they affect how the gas sort of, what the velocity field of the gas is.
Yeah. Have a quantitative way of finding these flux in simulation, or just seeing the quality of the lines?
Yes.
Maybe that's not, but I was wondering, have some diagnostics.
So there's, I think, no easy way to find a specific flux eruption event. But what you can do is use something like density as well as the the vertical magnetic field at the equatorial plane. So because the vertical magnetic field would shine up over here, and sort of scale that by radius somewhat, then this region would shine up. That's one way to sort of isolate, I think, an eruption. You should see the same thing over here. This entire thing would shine in vertical magnetic field strength. Recently we managed to do the same sort of magnetic acid disk simulation, but in very, very high resolution. And we were able to cross over to achieve such a high resolution such that we could resolve the plasma instability. So for example, like these spots over here, these are like over here, there are small scale plasmoids, like this little blobs of magnetized material, which sort of merge together. And these can give you high energy emission, like X-rays and beyond. And you can see some other points over here. And this was really enabled by the code that we use, Hammer, which is like Sean said, GPU accelerated. And we had like we injected extra resolution, at least in these parts. Now, when you ray trace that particular simulation, you get some interesting features, especially because of the magnetic flux eruptions. What I'm going to show you is, so this is again the mid-plane cross-section of that specific simulation. This is a black hole, even though it's white. And what I'm showing is the gas density. What you will see is that this region would be inspiraling. And when the flux eruption happens, there would be a whole region where the gas density would just fall. And this would be the corresponding image that you get out of it, the ray trace image, but for specifically M87 at 230 gigahertz. So yeah, so like you see over here, the gas is inspiraling. The waves over here correspond to those gas streamlines. And you see that's the magnetic flux eruption sort of happening. And at that point, what happens is gas from near the black hole gets expelled out. So the submillimeter flux goes down and you're left with the ring. It will play again. So the entire image actually becomes dimmer, but the fractional brightness of the ring becomes larger with respect to the surrounding emission. Now, this is very interesting because the ring is really determined by general relativity, and the thickness of the ring that can help us constrain what the exact, or at least help us to some extent get understand what the curvature of the spectrum would be in this case. And we wrote two papers regarding like what this image does. One was the image geometry during such a flare, because depending on where the exact flux tube is, at what point you're looking at it, the image morphology changes by a lot, because it's the disk becomes so non-axisymmetric. And then we also looked at the polarization features of this. Like you get a huge decrease in polarization fraction during this event. Yeah, so the brightness dips and the image becomes sharper. Other than magnetic flux eruptions, MADs are also very interesting. And at least the first reason why MADs got popular in general is because of the jets that come out of these simulations. MADs have extremely efficient jets, and it gives you a direct link to what the Blandford-Zanac process is. The Blandford-Zanac mechanism is a way you can actually extract the energy of the spin, or the spin energy of the black hole to power the outflows. So for example, what I've over here is a plot of the outflow power divided by the accretion power. So sort of output divided by input energies. And on the x-axis, I have the different black hole spins. Now, all of these black data points are individual geometry simulations, and all of them sort of calculate this particular parameter. And this dotted line over here, this black dotted line, that's what you expect out of standard sort of Novikov-Thorne sort of disk, which is radiating efficiently. Now, first thing that you see is that for positive spins, you get a very, very large amount of power already. So very, very powerful jets, but not only powerful, but very efficient jets as well. And the blue line over here, that's what you expect out of the Blandford-Zanac process. So as you go towards larger and larger black hole spins, the expected power that you get out of the mechanism out of the BZ mechanism matches what you get out of simulation, which is a direct confirmation, semi-direct confirmation of the Blandford-Zanac process.
Wait, how are you pushing power? Because you know the fifth just power, accretion power is,
And just accretion rate times c squared.
Radiated energy relative to f dot c squared. No?
So none of these are radiated. So this is the total.
Dot curve.
Oh, this one?
Dot curve is radiated energy relative to F dot C squared.
Yes.
But then are you normalizing the other curves and the points to F dot C squared? Is accretion power F dot C squared? Or
Yes. Is m dot c squared.
Okay. Because.
So that's why I'm calling it outflow efficiency, let's say. Now, the interesting part is, of course, because you have a larger amount of energy going out rather than coming in, mad jets, so jets for very highly spinning cases, actually spin down the black hole. And of course, because MADs have a particular saturation value of the magnetic flux on the black hole. So it provides a direct link between the input accretion power and the output jet power.
You're keeping the geometry fixed, right?
Yes.
It doesn't actually spin that you mentioned before.
Over here, yeah. In the geometry simulations, you don't change the space time. Yeah. But I guess the hope would be, like, of course, I'm saying spin down over here, but of course, the particular simulations that we do are geometrically thick disk simulations, which should happen at really sub-Eddington accretion rates.
Yes.
So probably the spin down won't be significant over the lifetime of the black hole, but where this would be really useful is when you have super Eddington disks, where I think the curves would be pretty similar in the case that you have very thick, geometrically thick disks over there. And at that point, you would have rapid spin down.
What are scales here? Because I guess that assumption, you need the assumption that you get a mad state through all the history that you need to get the spin down, right? Can you actually supply that? Because you need a continuous amount of flux into the black hole, right? To make that happen. So I was always curious about that. Like, is that like realistic or something that you expect?
I don't expect that the system would be supplied with magnetic fields throughout, like over billions of years. But of course, like there's no simulation which says otherwise, or like there are no intermediate simulations as of yet. What we have is actually like Sean's simulations of Sagittarius star, where we know at least for this current era of the black hole being fed by these Wolf-Rayet stars, you do feed the black hole with enough magnetic flux to generate the mad state. I think that's more or less robust, right? Yes.
But the accretion is like 10 to minus 7 Eddingtons.
Yeah.
Yeah.
10
10 minus 9.
Yeah.
Yes.
It'll take a long time.
Yeah.
Yes.
Okay.
Eventually, you might end up with this. But where was I going? Yes. Actually, I bring up that point in a little bit, I think. So because you have like such strong magnetic fields, what an important parameter would be the magnetic flux on the horizon, and that regulates what the jet power would be. So what we did with a bunch of undergraduate and graduate students is look at let's say you have the same surrounding ambient medium, for example this. You supply the black hole with a certain amount of magnetic flux and then see what the jet does. And what you do is look at what the jet morphology is, whether the jet shows interesting features other than like this shocked surface, this cocoon over here. And there's also this region of shocked gas, which is also pretty magnetized. So you have backflows. Now, what happens if you reduce the horizon magnetic flux? So, for example, over here, I'm cooling down the disk, and the amount of magnetic flux in the black hole magnetosphere goes down, and that reduces the jet power actually. And so you see that the jet is more wavy over here. It sort of breaks down a little bit, but it's still intact. For really, really weak magnetic fluxes, you have a very weak jet, and which sort of goes kink unstable. That is, it sort of cannot retain its shape anymore, and it blows out these huge cavities, which is filled with very hot material gas. So these are the particular students who have been working on this, and the main goal of the project is looking into what the shape of the jet is, at least out to galactic scales. And how does this depend on what the environment is, what the amount of magnetic flux given to the black hole is as well. And interestingly, most of the jets that we usually find in simulations have a parabolic profile consistently, like almost every other jet that we find in simulations have this parabolic profile. But when it comes to having an outside, like an ambient medium, and if you reduce the jet power sufficiently, you can also transition to a cylindrical type of a cylindrical jet, which is quite sort of interesting, because like Mojave has given us like a whole slew of AGN jets where they see sometimes transitions between parabolic to conical, but also they see cylindrical jets. So finding out at what point, what is the mechanism behind the change in shape between parabolic and cylindrical, or parabolic and conical, that was the main goal of this study. But from the particle acceleration point of view, because you have a change in shape, you might also have interesting features within the jet, like a change in the Lorentz factor of the jet, which might spark some amount of extra emission, which can come off as flares. Right. So the question of feeding the 5 minutes. Oh, okay. I went slowly than I imagined. Okay. So just this question about how do you feed the black hole with magnetic fields. What Sean found is that you can easily advect large-scale magnetic fields towards the black hole, and you transition to a magnetically arrested this state. And there was another paper led by Liska et al., where they found that even if you start with a toroidal magnetic field, a strong toroidal magnetic field, mind you, have a thick enough disk, you can form polar magnetic fields just from the dynamo effect. And so that simulation also transitioned into the mad state. So is there a way that we don't go mad, let's say? And for that, I was studying, I'm currently studying misaligned disk systems where the orientation of the incoming gas is not parallel to the angular momentum of the black hole. Right. So this is just an example of a simulation. The black hole is pointing in the z direction, and then there's the jet over here shown in blue, and there's the disk. Now, the interesting thing over here is that in the inner part, the jet sort of tries to align with the black hole spin, but of course, there's a disk in its way, so it bends away. And overall, that the jet aligns with the disk at large distances. Now, this is interesting because with the EHT, there's a possibility that we can detect misalignment, especially in M87, given that we resolve both the near horizon structure as well as the extended jet launching region. With the current, or with the 2017 EHT version, we couldn't resolve the extended features even if we tried because of noise. And basically all of these 3 different models, which are 3 different misalignments, would look virtually the same. But yes. Excellent question. So what we know about M87 is what the large scale jet looks like, what the position angle of the large scale jet is. In all 3 cases, what I did is I kept the large scale jet structure, or what the large scale jet looks like, the same. And because GR warps the inner disk when it's misaligned, that's why the inner images look different. And you can actually see the warp. So this is the warp.
Something to do with the jet.
It has?
Has something to do with the jet, the spine of the jet.
The misalignment of jet with respect to the line of sight. Well, the emission comes from the disk and jet boundary. So it has to do with both. So both the jet and the disk are warped. And that's what you are seeing over here. So over here, what I just wanted to quickly show is deviation from perfect alignment. So if you start out with a misaligned disk, what happens if we steadily increase the magnetic field strength? And what you see in general is that while the outer part remains misaligned with some degrees, we increasing the strength of the magnetic field sort of what it does is it tries to the jet tries to align the disk towards the black hole more and more. And in the case of a MAD sort of setup, you get perfect alignment always, even though the outer disk is misaligned. But of course, there are these two cases for very large misalignments where this does not happen. I think, would I end up there? Do I have time left? Okay. The aspect ratio of the disk is the disk scale height is around 0.3-ish, something like that.
I mean, there's multiplying mathematics that would show as you get close to internet, if you have a large aspect ratio, the slope becomes highly slippery, and that looks like it, you basically get part of it.
So this is not Bardeen-Peterson. Bardeen-Peterson occurs when your alpha viscosity is, I think, larger than your disk width. But this is the other regime. So this is the bending wave regime. That's the oscillatory pattern.
Well, it's still, I guess, maybe, yeah, it's occasional, but it looks like the slope increases.
You mean at the outer region?
Just when you get close to the
Yes. Yeah, the tilt does decrease, probably because of the bending wave, but also main issue in the bending wave analysis is that I think it does not account for magnetic fields. I think it's a hydro solution.
Yeah.
But what happens over here is that the jet becomes powerful enough to bend the disk. That's the difference. And that's also what happens over here. And so this is like the extreme case that I did where the black hole is pointing up, but the disk is directly in its way. So even
Is it more difficult to use the math at extreme misalignment?
yes. Did you only show them your movie? Aha. So I'll steal from him again. Same as Princeton. So this is the jet which appears, but then as the magnetic flux onto the black hole increases, the jet becomes more powerful. But when it becomes more powerful, it aligns and it blows itself out because it's blowing into the disk. So it sort of commits suicide. And that's why you see these intermittent bursts. How is this?
This is lovely, yes. It's more fun. Yeah.
Yeah. Now,
But here's another question then for Sean. If you're feeding the black hole wind, and there's not a lot of systematic angular momentum, are you ever going to get much of it back? Yes, we get it.
yeah.
So you still get that magnetic flux then? Yes.
Yes. It depends on how the jet, I guess, reorients the incoming gas somewhat.
It sounds like it could be pretty chaotic.
Yeah.
Yeah, can you go for a steady state in these type of simulations? Do well for.
So this particular simulation had an issue. So because it was a disk with a outside bound and the simulation had an outside bound. Yeah, it started with this big toroid, but then again you have an outside boundary. And because the jet is going into the disk, you eject part of the disk. And so you're also ejecting part of the magnetic flux. Now, if it was something like having continuous inflow from both sides, it may be more oscillatory. And maybe you don't get a steady state in that system. But I don't know, really.
Just to completely random thought, which always brings, when people study black hole binary systems, usually you see that when black hole spin, it's aligned with the angular momentum
Yeah.
of the orbit. And yeah.
Yeah.
Absolutely clear that happens.
So that's why I'm sort of pitching this as a possible, like this can happen in nature from maybe, yes.
But
Yeah.
in those systems, you're dealing typically connected with thin accretion.
In black hole binaries.
And low Earth state.
No, close to the black. Close to the black hole, you can touch you measure. That kind of mouse.
At high enough luminosity, yes.
But further out, there's a dispersed. I'm not
Yeah, it can be geometrically sick, I guess.
The third act is also right.
These things are all way below.
So,
The
wait,
accretion
yeah,
rates are way below.
there is no radiation in this
No, but I
system,
mean,
but
the accretion rate is way below the end.
that the internet is defined if you have
I understand that.
yes.
But just I'm saying, well, what is the thermodynamics? Do you know? It's not isothermal.
No.
It's adiabatic.
Adiabatic, yeah.
But, there's the quantum modality that exists, so energy is not speaking to finding systems. And we have two different states with the same overall velocity. So it's like a species system.
Yeah.
So those are sub-heading. I think it's not super sub-heading.
They're below 1%, right?
Well, where's bimodal? I think it's probably.
Like how subintense is it? Like below 1%?
And is it for a lot?
Okay.
Okay, maybe I thought it was a little lower.
Okay.
1 or 10% somewhere.
At that point, you'll probably get like pretty thin flows near the black hole, definitely.
Yeah.
Yeah. And then probably in that case, that there would be some amount of, there would be alignment because the body field does.
So I'm thinking about AGNs too, right? So like secret galaxies, accretion rates are typically a little above 1%. That's why they look to get this blue specter. But when they're a little lower, you tend to get more jets. They all have sort of jets, but they're not like really powerful jets. Like they're not radio loud, according to the damage, they're really loud. But they all have jets. And they're like I said, they're sort of 1 to 10% accretion rates.
Yeah.
This thing doesn't have a jet, but I mean, I don't know what the hell the alignment is. Well, actually, in some cases, you know, right? In like 1068, which is sort of a secret too. The disk is warped, you can actually see this. And the jet comes out in the inner part, it's aligned, but then, it's the main part of the disk is
Misaligned,
aligned.
yeah. So it bends away,
Yeah,
right?
and then,
Yeah.
and then the jet doesn't go crazy, it goes out like 30 parsecs to turns black.
We actually have seen those in some, so EHT has horizon sources, but it also has jet sources. And in some cases, like you just see that the jet moving on merely like this and then just breaking off at some point. But ooh, that's a difficult question. 10?
At least
10.
Okay, 2 and maybe
How-
some more.
You mean how many horizon scale images that we or how many sources? 10, I think, something like that. Yeah. And there's also, I think, some more data lying around which people are trying to get to. but usually like these are more calibrated sources rather than targets, usually, unless someone has a strong science case. Right. So this particular simulation is quite interesting because there's a lot of shock heating, lots of cavities. And I had one snapshot sort of out of the simulation. This is gas density, this is gas temperature, yes. And over here you see like the black hole spin is pointing up again, but the jet is sort of kinked out of the frame. Yeah. And this part over here, that's a cavity. So the jet has actually kinked and broken off.
There's an implication these bubbles that don't necessarily have very large Parkman motions, right? I mean,
Yeah, they get slowed down.
They're strongly magnetized, but they're partly buoyancy driven motion.
Yes.
Are this close in, there's already buoyancy driven, or do you know?
The issue is I don't know if the density profile over here is okay or not.
Right. We should just plot the entropy of your gas.
Yeah.
Right,
Yeah, so these are buoyant features in the simulation itself. These are buoyant
no, no,
features.
the gas volume.
Yeah,
But-
but
the issue is just that, obviously that when you're able to make measurements of the time commitment,
mhm.
and measure proper motions, so on, then you have much finer constraints with the model, but just an instantaneous snapshot.
Yes, yeah.
And so it sounds like there's a lot of promise there, and running the model can be stable.
Yeah, so that's all. That's one of the things that we want to do. Look at what the velocity pattern in the jet is. We haven't gotten into like looking into distorted jets all that much. More like these nice parabolic jets. I think this one is more difficult to do just because capturing this structure in a 3D simulation is very difficult. And of course, like looking at proper.
That is.
Yes, this is a 3D, and I was, so that's why it's just one snapshot. I didn't look at a movie. But yeah.
So maybe an obvious question, but how do you check that all that is like amount from the system, like of these cavities and all that?
How are they unbound? Like how to
Right,
check?
like if they're like yeah, mine probably in the central black hole, and
So
they won't fall back into.
the easiest thing is to look at a movie and see what these cavities do. The another thing that we can do is look at the Bernoulli parameter for this, specifically for this gas, and look at whether it crosses into the unbound. Yeah, I think, yeah, because the temperature is so high over here, the enthalpy alone would push it over the unbounded region. Yeah. But yeah, so these type of systems are very nice if you want to study, for example, particle acceleration events. For example, these two, so the jet edge is where you expect reconnection can happen. And this is, of course, a shocked region where they have another particle acceleration mechanism coming in. And finally, like, even if you have, even if you don't have such a distorted jet, even if it's nicely parabolic, at the jet edge, you can have jet boundary instabilities, which are magnetically driven, that can give you gas entrainment. And in a recent paper, we looked at whether that amount of entrainment and the amount of energy deposited in the gas can give you hadronic acceleration or not. And apparently it does. So nice. I'm proud, I'm way over time. So yeah, thank you.
Yeah, I'm trying. So in those, the flux tubes, do we have any idea like what should the actual density be there? Like, is it gonna be significant enough to reduce?
That,
emission? Because like in the jet, we really don't really know what, like it's probably like infinitely small, the amount of density.
yeah, it would, so the bulk of the flux tube, that's basically jet material. So whatever information you have about the jet particle density, that same would be for that. Hopefully the mixing that happens at the edges of the tubes are independent a bit. But you really need peak to, so particle cell simulations look into that a bit more and see whether there's a dependence on what the difference in densities is.
So your jets are initially pointing flux totally down.
Yeah. So they should essentially be like zero, right, and absent like particle sharing.
Right.
Yeah.
Which will show up eventually, but not in your sims yet. Right.
But actually, what magnetizations does the horizon region end up with numerically?
So the usual floor value that we have range from 50 to 100.
And
So
it pretty consistently reaches
P,
that. It pretty consistently reaches that. And
yes.
So much below it.
go much below it.
Oh, okay. So this is sigma.
Well,
Yes.
Now, you might be, you're talking about beta or sigma.
Yeah.
Sigma. So magnetization. Yes, what's that? Yeah.
Yeah.
So in the jet region, that's consistently at this floor value. The gas has much higher plasma beta in general. MADs particularly have like plasma betas of 1,
Yeah.
up to I think a few gravitational radii.
Yeah.
Sorry, did that answer your question? And
No,
Yeah.
so you basically be able to have handle magnetization about 100 these days.
oh yeah.
Yeah.
Usually you find like plasma beta of 100 at the outer parts of the disk. Like the reason you choose plasma beta of 100 as like the minimum plasma beta of 100 is because you usually want your disk.
Magnetization.
I think barely. 100 is barely, I think. Yeah. You want to make sure that you don't get spurious
Sure.
explosions with 100.
Negative kinetic energy, so.
Yeah. You don't want your entropy equation to sort of take things over, I guess.
So that number though is no longer dependent on your clearance. It's 50 to 100. That's a. It's like
More
converge. It's like-
There's a floor.
Well, it's just something you put in.
Yeah.
by hand.
Oh, you put it in by hand.
Yeah.
Yeah.
That's the for freezing.
Okay.
Yeah.
That's a floor. right?
Yeah.
Yes.
Sorry, good. That's what I want
So
to.
and then that floor determines like the Lorentz factor in the jet. and all that.
Yeah, exactly. Yeah.
Maximum Lorentz factor. So I did a study on what Lorentz factors you can have as a function of different floors, and usually if you don't get too much of distortions, like the Lorentz factor profile usually comes out to be relatively the same.
Even in terms of absolute,
Even stuff.
like in terms of absolute magnitude, it doesn't depend on.
Yeah. In general, I think, but of course, like temperature can do a lot.
The gamma that you get out of the jet doesn't depend on magnetization.
Yes, well, roughly, at least for the type of simulation that we do, which you roughly get gamma of like, depending on the collimation profile, 4 to 5 or so.
I see.
But if you have like a freely expanding jet, it will go on to
It will-
sigma. Yeah.
Okay.
But how fast? I think that is still unknown.
Well, we should probably let people.
Yeah.